I will talk about probability density estimation on the hyperbolic space and with an application to radar processing. So first, I will start by presenting three standard non-parametric techniques of probability density estimation. So histograms, kernels, and orthogonal series. Then I will make a very small introduction to the hyperbolic space and the Poincaré disk. I will follow by a presentation of how to apply this three density estimation technique to the hyperbolic space. And I will conclude by a potential application to radar processing. So first, histograms. This is the simplest non-parametric density estimation. The space has to be cut in a set of bins, and the estimated density is obtained by counting the number of samples in each bin, and then we divide by the size of the bin. Kernel density estimation is also quite simple. So we place a kernel of integral 1 over each observation, then we sum all the kernels and we divide by the number of samples. And now orthogonal series, it's slightly more complicated. Here we want to study the density through an orthonormal basis of function. And it's quite simple to estimate the scalar product between the density f and a function given a set of samples. And since the basis of function is orthonormal, the scalar product are the coefficients of the decomposition in this basis, then it's possible to estimate the density f by reconstruction using the estimated scalar products. And with the appropriate choice of orthonormal basis, this method is equivalent to the kernel density estimation. So now just a general consideration on density estimation. So the estimation should be as homogeneous and as isotropic as possible. When we have no prior information on the density. So this means, for instance, that with histograms, bins need to have shapes as similar as possible, and the bins should be as round as possible. So the same goes for kernels and orthogonal series. However, on this small example, if the underlying space is a disk, we are working on a space which is not homogeneous, and an Euclidean disk which is not homogeneous or isotropic, then the estimation cannot be exactly homogeneous and isotropic, but the general idea is to be as homogeneous as possible and as isotropic as possible. So now the hyperbolic space, or the two-dimensional hyperbolic space. So this is, we can see this as the only two-dimensional manifold of constant negative curvature. And we will be working here with the Poincaré disk, which is a model for the hyperbolic geometry of dimension 2. So this is a two-dimensional open unit disk with the following metric. So the distances are basically increasing as we reach the border of the disk. And this space is homogeneous and isotropic. So on the contrary with the Euclidean open unit disk. So now how do we apply these standard density estimation techniques, so histograms, kernel, or orthogonal series, in the Poincaré disk or in the hyperbolic space? So first, histograms. to make good histograms, we need to have some good tiling of the space, and a good tiling, so bins should be as similar as possible to each other. So there are various regular tiling on the hyperbolic space. So here are 3 different examples. And the main problem is that there are no homothetic transformation for every scaling factor in the hyperbolic space. So it means that given a tiling, it's not possible to rescale it as we want. And now when we are dealing with different phenomena, if you want to estimate different densities, and if we have a different number of samples, we will always want to rescale the original tiling. And then it means that we have simply to change the tiling, so which is not very convenient. So we didn't push the study of histograms on the hyperbolic space. For orthogonal theories, so standard choice for the basis of function is to take functions among the eigenvalues of the Laplacian operator. So in Rn, this gives the Fourier basis. And now if the density is defined on a compact interval, we get some Fourier series. While if we're working on a non-compact domain, like from R to R, we have a Fourier transform. It means that in one case, we will have to estimate a sum, and in the other case, we would have to estimate an integral, which is quite different in terms of computational time. And on the hyperbolic space, we only have expressions of the eigenfunction of the Laplacian operator when the function goes from the disk to R, and we don't have any explicit solutions for function defined on a compact domain of the Poincaré disk. So it means that if we want to use this method, we will have to go through the estimation of an integral, which is not very convenient. So now the kernel density estimation. So let K be a function from R plus to R plus with a few decreasing properties and with a bounded support to his computations of the convergence rate. So here you have the standard Euclidean kernel density estimator. And now if you switch to a Riemannian manifold, you are tempted to first change the distance inside the kernel. The problem is that if you just do that, the kernel do not integrate to 1 anymore. And you need to take into account the volume change induced by the exponential application going from a tangent plane to the manifold. And once you computed this volume change, you can build another kernel density estimator, which was first proposed by Peltier on more general manifolds. In the case of the hyperbolic space, the expression of this volume change is not very difficult to compute. So if we take an expression of the hyperbolic metric in polar coordinates, which is a standard expression, we can find the expression of the volume measure. And now we just have to switch back to from a polar parametrization to a Cartesian parametrization by dividing by the radius. And so we obtain the term of volume change of the exponential application. So we obtain this kind of kernel on the hyperbolic space of dimension 2. And if we formulate this estimator as a convolution, we can see that equivalent to the orthogonal theory method when using the eigenfunction of the Laplacian. So, except that now we don't have to go through the estimation of an integral, and we have just the standard cost of the kernel density estimation. Now I will present a potential application to radar data. So the radar data are composed of a succession of inputs, Z, which are vector of C power n. So, and now the natural question is, Z, is it a reflection from the background, or is it a reflection from an interesting target? Or, and then we might want to do some classification over the vector Z. So we make several assumptions. First, we assume that the Z is a centered Gaussian process. So we can define it by its covariance matrix. Furthermore, we make some stationary assumption, and then it makes the covariance matrix Toeplitz. So using the autoregressive model, we can define some reflection coefficient, which will form a new parametrization of the space of Toeplitz covariance matrices. And the interest of this new parametrization with reflection coefficient is that the metric we are working with on the space of Toeplitz covariance matrices become diagonal. And it's actually a product between the logarithmic metric on R plus and n minus 1 times the Poincaré disk. So now let's assume that you have multiple acquisition of the same background. You can be interested in the distribution of the reflection coefficient associated to this background. And then it can potentially be used for classification or identification of non-background objects. So it's really a preliminary application. So here you have two different examples which represent two different environments. The first row is the reflection of the ground. The second row is the reflection of it's an acquisition in a rainy environment. And so the weird spot on the first image is just due to the normalization used to ease the visualization. And so we can see that the densities looks quite different. It's possible to perform segmentations. And it's supposed to, at some point, help some classification operations. So to conclude, the density estimation the density estimation on the hyperbolic space is not a very difficult problem, but it's interesting to note that the histograms and the orthogonal theory density estimation problem present some technical difficulties, and that the kernel density estimation is the easiest solution. And future work will focus on deepen the application to radar signal and performing actual classification. And we'll also focus on the computation of the volume change for other spaces. So thank you for your attention.
Okay, so thank you, Emmanuel. And if anyone has questions, please.
When you say that there's some difficulties with the integration on the Poincaré disk, do you mean that there's no quadrature formula for this manifold?
I'm sorry, I didn't get the question.
When you're trying to compute a Fourier series or whatever, or for example on the sphere, first thing you need to do is sample where you're calculating the points, where you estimate your density. You have to do that as well.
Could you just speak louder?
Ah, sorry.
I don't.
When you compute an integral on
Yes.
a manifold,
Yes.
say for example the sphere, you first choose where you compute the values of your density, right? That's computational.
Yeah, you select the domain.
You pick up the points, and then in order to do that, you sample the sphere or you sample your manifold. And then you have quadrature formulas saying that an integral can be approximate or can be sometimes equal to a certain discrete sum. So this type of result exists on the sphere, for example. I was just asking if it was the issue here. Is there a way to sample the Poincaré disk and then compute exactly or approximately an integral on this disk? That's.
I must say that I cannot answer for sure. I don't know.
I don't know either. So that's why I was asking. I don't know either, so that's why I was asking.
Yeah, it could be something interesting to look at.
I don't know. Sorry. That's okay.
No, it's probably an interesting question.
Yeah, maybe it comes from that thing. I don't know.
So yeah, I will investigate that question.
Okay, thanks.
Thank you. Any more questions, please? Well, yes. Can you pass?
My question is about tilings. Why do you want to tile into polygons? Is it just because of this homogeneity you want, or?
Yeah, I was basically looking for some regular tilings, and so there are various polygonal tiling on the hyperbolic space. So the first thing I did was try to understand how this worked, and so this kind of tiling could be very interesting to compute histograms. But there are actually two problems with this tiling to compute histograms. So the first one is that given a polygon, when you make all the tiling, you cannot always rescale this polygon. And the second one is that if you have the coordinates of some sample, it's not instantaneous to obtain or to identify the bin in which it lays. Do you see what I mean? Or it's not, if you have like a square tiling of the Euclidean space, if you have the coordinate of a point, you can directly identify in which square it lays. And it's not the case here. So
there is no easy tiling starting with a circle in the center.
There is
no, because here the problem is that if you scale, you change the number of sides of your
yes,
polygons.
if you actually...
Is there any tiling starting from a circle in the center?
Like a tiling made of circles?
Yeah.
Yeah,
circle will be in the center. The other ones will not be really circle.
Oh, you mean, but all, bins of different shapes?
Yeah, so like you take some discrete group of your isometric group of your Poincaré disk, and you start with something which is a circle in the middle. I mean a disk in the middle, and then you act with your discrete group and hope that you will get tilings. Might it work?
I'm not sure that
Okay.
I understand. I'm sorry.
I think we may have time for one more question, please, so before going on.
justification of why using this.
Why using this? You mean why?
This kind of
But you mean why using the hyperbolic geometry or why using a polygonal tiling? The thing is, why using a polygonal tiling is that it's because it gives regular tiling. So they have some homogeneity property, and
it relates to some kind of clustering where the distances become smaller and smaller if you go off the center. That would be an intuitive justification to use something like this.
but I have the feeling that what you say is related to the metric more than the polygonal. Yes, but then the metric will be related to the repartition of the data we are looking for. Yes. But,
Thank you. Okay, so thank the speaker again, please.